in the UK, after which I worked for 4 years at a company called Tech. They do process simulation software for the chemical industry, so called ESS, and then was renamed to Helmholtz G stuff, and after that it was Helmholtz right. They are working in the Institute of Membrane Research, so partner institute of the Institute of Hydrogen Technology, and I gather you already heard some presentations from those guys, and I hope they introduced what Helion actually is. We belong to the Helmholtz Association as well, as DIR does, but we are about an order of magnitude smaller in terms of employees, so we've got about 1,000 employees. And as I said, 50 of those employees work in the Institute of Membrane Research. And with that, I would like to start my presentation here. I'm going to introduce what we are doing with membranes, what we do in general, introduce what we do with respect to hydrogen separation membranes, then transport mechanisms that are dominant in membranes, look what we do with the membranes once we have them in terms of putting them into a process, how to model and simulate their operating performance, touch on some application examples and then I'm going to summarize and finish. What I have to say is there are a lot of types of membranes around. My talk will be a polymer-centric perspective. So there are other membranes as well that can be used for hydrogen separation, but I'm going to talk about polymeric. Right. What we are doing is, I'll skip this one. What we have in our institute are several departments, because we cover the whole research and development pathway from the material science of what type of material, polymer in our case, you can use to separate hydrogen from a gas stream or separate impurities from a hydrogen containing gas stream. So we look into what materials are good candidates for that, how to make membranes from those materials, how to design the pressure vessels into which these materials are being fit into, and how to put that into process, how to scale up the membrane production, and so on. So that is covered by the different departments and the different people you see there. And this is going to this is showing what we exactly do. Now I'm trying to find you. Oh, this one. So as I said, we start with the actual polymers. We make membranes, so that's a membrane production machine here. We put them into membrane modules. These are membrane modules. Use these membrane modules in turn to put them into pilot plants. We design ourselves and operate them in close to realistic scenarios, or even sometimes in side streams of industrial feedstocks. We also look into modeling and simulation, so how to really depict these membrane modules in process type simulations, where you can really look into how these membranes behave in a process, how the modules behave in a process, and how to design competitive membrane unit that separates hydrogen from gas stream, or that purifies hydrogen. And of course, we also look in how well the predictions from our models compare to the results we get from our pilot plants, whether we are not simulating some sort of garbage. So that's what we in general do. So as I said, we cover the whole research and development pathway. Well, with respect to membranes in general, they've got a large type of potential, and that has been recognized for hydrogen quite early on. So if you look at gas phase separations by membranes, really it started with hydrogen. So the first applications were in the early 1980s in the big, large-scale industrial sites where hydrogen is being used. That's ammonia, Haber-Bosch processes, that's refinery processes, so anything with catalytic crackers and so on, wherever you have hydrogen in there, hydrotreaters, you've got large gas streams containing hydrogen. You would like to reuse the hydrogen within these refineries, for instance, or big chemical plants, and there you use membranes to recycle the hydrogen. And the same goes for methanol. Why you do that? We already heard pressure swing absorption you mentioned. That's a big competitor, but for some instances, membrane technology is actually the better way, the more cost-effective way to get your hydrogen streams. You've got basically a steady-state process. Pressure swing absorption is intrinsically dynamic, has a lot of moving parts, and it's quite large when you build it up. So you've got a modular plant design that's much smaller. So you can really easily integrate it with existing processes, and you've got, well, basically also a lot of uses in the hydrogen technology or in the hydrogen economy that's being built up, because you've got already a lot of experience, you've got a lot of membranes, but you have to sort of look into how to fit that into these new systems. And as the last point here, most of the hydrogen membranes are hydrogen selective, but it's more than just that. There are other membranes as well that can do a lot of good jobs in that respect. What you see on the picture here is one of the pilot plants we have at Gesta. That's a membrane module for sort of mini plant and pilot plant uses with around 1 square meter. Well, here's the quite busy map of industrial applications of hydrogen. So you've got the big industrial things like steel, like chemical industry, like the whole CO2 utilization power-to-X scenarios, where you've got hydrogen processes involved as well. And wherever you see these colored boxes, you've got membranes that can do something to hydrogen. Now, the colors do not mean the sort of color coding, blue hydrogen, green hydrogen, red hydrogen, turquoise hydrogen, and so on, or gray hydrogen. They're just there to point that out. For example, you can use hydrogen in steel plants to recover from the coke gas or the blast furnace off gases. You can recover hydrogen using membrane technology. Of course, you can do something with hydrogen that you get from biogas sources. Remove the carbon dioxide, for example. You can put the hydrogen into a natural gas grid and recover the hydrogen from there and put it to other uses. You can, of course, as I already mentioned, close circuits within the chemical industries and also within CO2 utilization processes. Now, hydrogens or membranes in general, these are actually examples for CO2 selective membranes, come in a lot of different sizes. So this small guy down here is a membrane module connected to a small biogas plant. And these are all membrane modules as well that are being used for carbon dioxide separation from natural gas. So there are a lot of different sizes of membrane installations that you can basically plug together in a modular fashion. For a membrane process to work, you don't only need the membrane and the membrane module is separated, so the membrane is installed in. You need something more to it. In order to convince a molecule to pass through a membrane, you need something like a driving force. The driving force is generated by pressure, so you quite often will have a compressor. Membranes are also always, or the transport of membranes is a function of temperature, so you adjust the temperature. You don't want to have any condensates on top of the membrane, so you remove them. As I said, you adjust the temperature. You don't want to have any particulates either, so you've got a filter. And then you come to the actual membrane system itself. That separates the feed gas into a high pressure product, that's the retentate, into a low pressure product, that's the permeate. And sometimes we even apply a vacuum here to even more increase the driving force and adjust the pressure ratio. So you've got a lot of different elements that fit into such a membrane process. Now I mentioned you have different types of membranes. So you could have the sort of standard, quite often these are polyimide type membranes. They preferentially permeate hydrogen compared to, for example, methane or nitrogen. And what you will see is that if you enter a membrane module here with some, say, 20% of hydrogen, you will see that the hydrogen content falls when you move along the membrane area. But you can also might have a gas stream that contains hydrogen and carbon dioxide. And then there are carbon dioxide selective membranes that would allow you to separate the carbon dioxide from the hydrogen. So you see dropping carbon dioxide profile. And there are other membranes, they preferentially permeate higher hydrocarbons, butane, pentane, or vapors of pentane, hexane, and so on. And or even toluene and these sort of things. So you will see that these higher hydrocarbons will drop as you move along. So you can select the membrane material within reason. So there are not membrane materials for every single thing, but within reason you can select the membrane material that separates either the hydrogen from the gas or the impurities from the hydrogen. Now, what are the membranes for hydrogen application? So if we look at membranes in general, we've got a map like that. It's a selective barrier between two phases. What we are talking about are synthetic membranes, and they are solid. Now, they can be organic, like the polymers I'm talking about, or they can be inorganic. These might be zeolites or palladium, silver alloys that are also hydrogen selective. They are either homogeneous, meaning they are made from one and the same material, or quite often they are heterogeneous. So you've got a thin hydrogen selective, or carbon dioxide selective, or whatever selective that is applied to a porous support structure that gives you the mechanical strength of the system. And that means they are asymmetrical as a membrane. Now, I said I'd talk about polymeric membranes, but there are a lot of other membranes as well. Most prominently are palladium alloy type membranes. The cool thing about these guys is the hydrogen you get on the low pressure side is really, really pure. So any impurity will only pass by defects through this membrane because the hydrogen is being adsorbed on the surface of the palladium, split into atoms, and transported through the palladium layer by means of sort of like moving from one lattice point to